chemically represented as hydrogen borate, is a weak monobasic Lewis acid comprised of boron, oxygen, and hydrogen. It has been utilized for various applications since ancient times, particularly in agriculture and industry. In the pharmaceutical sector, boric acid is recognized for its antiseptic, antifungal, and antibacterial properties. Its effectiveness in treating infections and its role as a preservative in formulations make it a valuable compound in medical applications. This study highlights the detection of boric acid in various pharmaceutical formulations in the pharmaceutical industry.
The material required for chemicals is boric acid, hydrochloric acid, glacial acetic acid, methanol, ethanol, tetrahydrofuran HF, hexane and double distilled water. For the instrument is UV vis spectrophotometer and analytical balance. Next, the instrumental setup for spectrophotometer. This setup involving 3 steps, which is the first one is set the wavelength to the desired wavelength needed, second set the blank, and lastly measure the sample. And remember, do not touch the part of the cuvette that the light through because the fingerprint can interfere with the absorbance readings.
First solvent is water. To prepare the aqueous solution, it started with accurately weighed 20 mg, 25 mg, 30 mg, 35 mg, 40 mg, and 50 mg amounts of boric acid powder. Each amount was then dissolved in double distilled water to prepare 1 ml of boric acid solution at varying concentrations. It is important to handle boric acid with care. So, wear protective gloves to avoid skin contact that can cause skin irritation. Next, 100 microliters of boric acid for each concentrations were taken and was diluted up to 3 ml with double distilled water. This step ensured that each sample was properly prepared for analysis. Finally, the diluted solutions were used to obtain the UV vis spectra of boric acid in aqueous solution.
Method of preparation of alcoholic solutions of boric acid. Accurately weigh 20 mg of boric acid using analytical balance. Dissolve it in 1 ml of alcoholic solution. Next, take 200 ml of the stock solution and dilute each to 3 ml using ethanol and methanol respectively. Thus, the result solutions were prepared successfully for UV vis spectral analysis.
Boric acid solution was prepared by using 0,2-MHCl solution. For this 20 mg of boric acid was accurately weighed and dissolved in 0,2-MHCl solution so as to get a solution up to 1 ml. This solution was further diluted by taking 200 micro-L of the solution and diluting it up to 3 ml using 0,2-MHCl solution. The resulting solution was used for carrying out the UV vis analysis of boric acid solution prepared using 0,2-MHCl solution. These are precautions must be taken to ensure accuracy and safety. First, 0,2-MHCl is a dilute acid, but it can still cause irritation. Always handle it with gloves and safety goggles in a well-ventilated area. Please ensure all glassware are clean and free of any contaminants, as impurities can interfere with the UV vis readings. After that, when diluting up to 3 ml, mix the solution gently to avoid introducing air bubbles, which can interfere with spectrophotometric readings.
20 mg of boric acid dissolved in glacial acetic acid to get 1 milliliter of solution. The solution is shaken vigorously for 5 minutes to get the maximum solubility. It then left undisturbed for 30 minutes to let excess undissolved boric acid to sediment. Then separate it from the supernatant. 200 microliters of the supernatant further diluted up to 3 milliliters by using glacial acetic acid. UV-vis analysis was done using the solution.
1. 20 mg of boric acid mixed up with THF solution as it reach 1 ml and being dissolved. 2. However, there will be still undissolved boric acid, and it continues to be shaken within 5 min. Continue with kept it undisturbed for 30 min. 3. The undisturbed solution was next filtered to obtain the supernatant. 4. 200 microl of supernatant is obtained and diluted to 3 ml by using THF, and is ready for the UV-vis analysis. 5. As a precaution PPE, such a proper face mask must be used as it is prohibited to inhale or ingest both chemicals due to their volatileness.
20 mg of boric acid powder was measured, and then it will be dissolved in hexane to make a 1 ml solution. The solution was mixed by shaking it vigorously for 5 minutes to maximize solubility and will be left undisturbed for 30 minutes to allow sedimentation to happen. Then, the supernatant, which is the clear solution, will be carefully separated from the sediment. Last but not least, 200 microliter of the supernatant was taken to dilute it with hexane up till 3 ml. The solution was then ready for the UV-vis analysis.
This is for solubility profile of boric acid in some solvent that includes solvent system, temperature and boric acid percentage by weight in saturated solution. The solubility profile here means how the boric acid solubility changes under varying temperature from different solvents. In this case, the solvent system used are water, ethanol, methanol and glacial acetic acid. From the table, it was observed that methanol and ethanol gives the highest percentage due to different on-molecular interactions between boric acid and the solvent's molecules. As we know, boric acid is a weak Lewis acid and fairly soluble in water because proton was not produced, and lastly due to the high temperature. Solubility of boric acid increases as energy overcome the intermolecular force. This is the observed solubility of boric acid in different solvents, where in this experiment, they used water, 0.2 mHCl solution, ethanol, methanol, glacial acetic acid, THF and hexane. It was observed that water, 0.2 m of HCl solution, ethanol and methanol, the solubility was completely soluble, where glacial acetic acid is partially soluble and THF and hexane has very slightly soluble.
Based on the UV-vis spectra, aqueous boric acid solution gave negative absorbance in its UV-vis spectrum except for the concentration of 0.67 mg/ml. This is most likely to be due to the formation of polyborates at higher concentrations in water and thus gave a negative absorbance at higher concentrations. The spectrum also displayed a broad dip with overlapping features. This characteristic is attributed to interactions between boric acid and water molecules. Such interactions can alter the electronic environment of the system, leading to changes in the absorption spectrum.
The data results shown positive absorbances and absorbances peaks around 200 nm range. The positive absorbance can be accounted when boric acid is dissolved in ethanol. Triethyl borate is formed in equivalent amount as that of boric acid and may thus give a positive absorbance. The small peaks around 200 nm range correspond to minor electronic transitions or impurities, but they are not indicative of significant light absorption. These results imply that boric acid in ethanol does not undergo substantial electronic transitions in the spectral range, making UV-vis spectroscopy less effective for analyzing boric acid directly.
For UV-vis spectrum of boric acid solution in methanol, The data analysis from the spectrum shows clear spectra without any crowding and also shows positive absorbance where the peaks at the range of 200 nm. This is because the methanol is an alcoholic solution in which also a polar solvent that enables strong hydrogen bonding between boric acid. Also, methanol contains hydroxyl groups where it could be bonded with the hydroxyl group of boric acid. Thus, hydrogen bonding between these two could stabilize boric acid in methanol solution.
Acidic conditions can lead to the protonation of boric acid or influence its electronic structure, making it absorb at certain UV wavelengths. The observed peak around 200 nm could be attributed to the electronic transitions of boric acid or its interactions with the HCl solution. Boric acid does not exhibit strong chromophores that absorb in the visible. The spectrum indicates a sharp peak around 200 nm. This peak suggests the presence of a significant absorbance within the ultraviolet range due to electronic transitions associated with the boric acid molecule when dissolved in the acidic medium. Apart from the peak at 200 nm, the absorbance remains relatively low and stable, indicate minimal absorption at higher wavelengths. This stability can also imply that boric acid does not have strong absorbance outside of this UV region when dissolved in 0,2-MHCl. The presence of 0,2-MHCl likely alters the electronic environment around boric acid, which may affect its absorption properties. Acidic conditions can lead to the protonation of boric acid or influence its electronic structure, making it absorb at certain UV wavelengths. The observed peak around 200 nm could be attributed to the electronic transitions of boric acid or its interactions with the HCl solution. Boric acid does not exhibit strong chromophores.
The data observed shows that the spectrum have a wave-like pattern, which in turn giving it a positive and negative absorbance. The absorption peaks, as can be seen, is in the UV range, around 200 to 240 nanometer. Glacial acetic acid is polar aprotic solvent. It does not participate in hydrogen bonding the same way water does. Because of this, it affects the ionization of boric acid and potentially lead to a different absorption behavior in the UV-vis region. The absorption band around 200 to 240 nanometer are due to the electronic transitions associated with the boron-oxygen bonds. Particularly, if boric acid forms ester-like structures with the acetic acid molecules. When in complex form, these transitions could be modified by changes in the ligand field around the boron center. The UV absorption peaks shifted to a longer wavelengths is probably due to the shifted absorption maxima. The solvent environment affects the electronic structure of boric acid, causing it to shift.
The spectrum has positive absorbance values, indicating that boric acid effectively absorbs UV light in hexane. Hexane, being a nonpolar solvent, introduces minimal interference in the UV-vis spectrum, making the measurements cleaner and more reliable. Due to the low solubility of boric acid in hexane, there is minimal formation of polyborates, which helps maintain a simple and interpretable spectrum. Hexane is a nonpolar solvent, meaning it lacks partial charges and cannot form strong hydrogen bonds or dipole-dipole interactions with solutes. Boric acid is moderately polar due to its hydroxyl groups, which can form hydrogen bonds. This polarity mismatch between boric acid and hexane leads to weak interactions between the solute and solvent. Because of this mismatch, boric acid has very limited solubility in hexane. Most of the boric acid remains undissolved, resulting in a saturated solution with minimal boric acid molecules interacting with the hexane solvent. Despite the low solubility, boric acid can exhibit measurable UV-vis absorbance in hexane. This occurs because of weak van der Waals forces between the boric acid and hexane molecules. These weak interactions are enough to allow boric acid to exhibit characteristic absorbance in the UV range, though the absorbance may be weaker and less distinct compared to polar solvents.
1. By looking at the spectrum given, it is noted that there were positive absorbance and multiple peaks as the data obtained. 2. It explains the weaker absorbance and lack of strong shifts in absorption spectrum. 3. From that observation, it is due to the polarity of the THF itself, which is moderately polar. 4. THF lacks hydrogen bonding and thus limits certain types of solute interactions that would be common in strongly H-bond solvents. Therefore, interaction with boric acid will be less intense and less stable, making it much less preferable to be as the ideal solvent with boric acid.
Next, comparison of solvent. As we know, boric acid is weak acid and primarily soluble in polar solvents. It forms hydrogen bonds and dissolves better in solvents with hydroxyl groups O or similar polar groups. Therefore,
in conclusion, this study highlights the identification of boric acid in various solvents within the context of the pharmaceutical industry. The findings demonstrate that boric acid's solubility and UV-vis spectral behavior vary significantly across different solvent systems. Polar solvents such as water, methanol, and ethanol are most effective for dissolving boric acid, which is crucial for its application in pharmaceutical formulations requiring precise solubility and stability. The analysis also emphasizes the limitations of nonpolar and less polar solvents like hexane and glacial acetic acid, which offer reduced solubility and less favorable interaction with boric acid. These insights are instrumental for optimizing the use of boric acid in pharmaceutical products, ensuring its effective incorporation into formulations for antiseptic, antifungal, and preservative purposes.